different ways of looking at Interstellar. Interstellar, the stars are on average 5 light years apart. The nearest stars to us are 4.3 light years. And we can think of several ways of building machines that can get there. The first is using light. So light from the sun is solar cells, momentum transfer, pressure from the solar radiation pushes the cell. As you get further away from the sun, of course, then you lose that intensity. So instead, you could use lasers or microwave beams to push a cell even further. But in my opinion, this is really appropriate for much smaller masses, small payload masses, but getting there potentially quickly. And that's what the Breakthrough Initiative Project Starshot was doing, was looking at those kind of small probe masses. Now, another way you can do interstellar is with reaction engines. That includes fusion propulsion, but it also includes things like antimatter catalyzed fusion. Antimatter catalyzed fusion and antimatter are somewhat speculative because we don't know how to contain antimatter, let alone how to mine sufficient quantities of it. They make something like a few nanograms per year at CERN in the particle collision experiments. Fusion is much more credible because we know how to do fusion. We know it works in the sun. We have a good handle on it. And in fact, the National Ignition Facility in San Francisco only a couple of years ago successfully got ignition in a laboratory. So that's pretty exciting. It gives us not just physics, but engineering credibility. And so I'm particularly interested in applying fusion to machines that can travel to the stars. There's other more speculative ways of getting to the stars, such as space drives. That's using the properties of space itself in some way to mine it. So you don't have to carry massive propellant tanks along the way. And there's an even more speculative approach, such as using general relativity, warp drives, and wormholes. We tend to think that the speed of light is the fastest thing, 300,000 kilometers per second. But actually, special relativity allows for space itself to go faster than the speed of light, superluminal. And this is what we think happened at the beginning of the universe, for example, when the universe underwent inflation. So I looked at your slides and they're very good, very, very high quality. So well done. I hope you enjoyed looking a bit at this subject. My main comment is most of the propulsion systems that you identified were interplanetary applications. So if you look at the sort of velocities you were coming up with, there were tens to hundreds of kilometers per second, which is insufficient for interstellar missions. Really, we need to be hitting something like 10,000 plus kilometers per second to get to the nearest stars in of order a century or two. Beyond that, can our materials survive that long? We know the Voyager probes have been in space since 1977. They're still functioning. Voyager 1 and Voyager 2 are out there in the past the solar heliosphere, still transmitting information. But how far can they survive? The reason they will switch off, of course, is because the power supply will run out on the RTGs. But your slides were really looking at interplanetary systems. The other thing is there's a lot of fusion companies springing up, fusion propulsion companies who are claiming that they have fusion engines, and this remains to be seen. Just because you can measure some neutrons coming out of reaction, that doesn't mean you've got ignition according to what's called the Lawson criteria, where the product of the confinement time of your plasma, the number density of your particles, and your temperature has to be more than a certain number. You can look up what that criteria is. So really, we need to be hitting the speed of something like 10,000 kilometers per second. And for fusion, in fact, you can work out that the maximum possible speed you can get from fusion reactions is about 45,000 kilometers per second, about 15% of the speed of light. And that includes staging. It includes using anetronic reactions like deuterium helium-3, where you get protons and helium-4 particles, which you can use in a magnetic nozzle to direct for thrust. Any neutrons you're getting out of those reactions is bad news because that radiates the structure. And although they're called anetronic reactions, actually about 15% of the energy deposition is due to side reactions, such that deuterium will react with itself and produce tritium, which produces neutrons. And you have to account for all of that. The other thing is spacecraft, they get very hot because these are very hot engines. It's particularly if you're pulsing, like 100 times a second each time you're firing lasers. And so they have to get rid of all that heat. And so they need massive radiators, okay? So really it's spacecraft design of these sorts of nature are a problem in thermal management. And that's something you have to really think about. Just think a little bit about kinetic energy. Okay, if you had a 1 kilogram probe, let's call that the minimum possible probe. We've actually looked at things much smaller than that on the gram scale, but let's go for 1 kilogram. And you wanted to accelerate to 1% of the speed of light. This requires a kinetic energy of something like 4.5 times 10 to the 12 joules. If you want to send that to 10% of the speed of light, then you're looking at 10 to the 14 joules. Okay, but that's a very small probe, maybe with some microelectronics and a camera on it. Let's say we want to send something much bigger, like 1,000 tons, which begins to approach the large kind of probes we need, which might take humans on board. Sending out at 10% of the speed of light, 1,000 tons, you're looking at 10 to 20 joules of energy. Now, the actual global energy consumption of the planet today is something like 6 times 10 to 20 joules of energy. So it's comparable to that. And that's just 1,000 tons. So if you wanted to send something like a world ship or a crewed vessel with hundreds of people on board, like you see in science fiction, that may be hundreds or thousands of tons, you're looking at energy levels which exceed global energy consumption today. And therefore that comes into the argument of the economics. Is it ethical, for example, to build a starship and go off on a jolly to the stars looking for exoplanets and potentially ET, when you've still got all the problems on Earth, global conflicts, disease, pandemics, all that sort of stuff. So, investments in space programs is not particularly large. At the peak of Project Apollo, it was something like 4.6% of the gross national product, which is still quite small. And today it's less than 0.5% of America's fiscal budget. So we don't spend a lot on space. But, in order to do something like an interstellar mission, that certainly requires an international effort, and it certainly requires probably some billionaires to get involved who are interested in pushing that technology. But even if you can send something like 1,000 tons, then you have to ask, well, can I get to 10,000 kilometers per second plus with that kind of mass? What kind of engine could I fit into that? So if you take, for example, the mass ratio, so mass ratio is given by the exponential of the velocity increment over the exhaust velocity. If we assume an exhaust velocity about 10,000 kilometers per second, which is what we need, and if we assume a delta V of about 12,900 kilometers per second, which is commensurate with 4.3 light years over 100 years, then this suggests a mass ratio of something like 3.63. That's just for a flyby, okay? And that will get there in sort of a century or two. But then if you want to go rendezvous, you want to decelerate, you have to square the mass ratio. So now you're looking at r squared, which is 13.17. So, and then you can work out from the mass ratio m naught over m final, roughly that implies about 13,000 tons of propellant is what you would roughly need. So, and if you're talking about helium-3, where you're going to get that from? Well, you have to go to gas giants, you have to mine it, or the solar wind, or the lunar regolith, which is a huge architectural project. And this pushes out the timescale to first launch. Okay, so that's the first thing to think about. And then, even with 1,000 tons, that has to include your payload, your structure, your heat radiators, anything else that's fuel of your engine. And, for a fusion engine, all the papers I've looked at suggest the minimum mass is of order 300 tons is what you would get away with based on current technology, if we can make it work. So let's just have a look at a couple of spacecraft designs. This is Daedalus. Okay, this is a nice model of Daedalus that I have. I actually had this built in Russia. So Daedalus was a project of the British Interplanetary Society in the 1970s. And you can see it's a 2-stage system. You remember Saturn V that went to the moon? It was a 3-stage rocket. This is a 2-stage engine. And it goes like this. So it launches from actually out at Saturn. It's got these massive propellant tanks on it, which is 50,000 tons deuterium helium-3. It's got this is the payload here, which is an artificial intelligence probe, 450 tons. It's got a beryllium particle shield, about 50 tons on front. It's got this huge engine reaction chamber, and you can see all of these electron diodes. These are the laser beams around the outside edge. And the idea is that it basically injects tiny particles of deuterium helium-3 onto the axis, and the laser beams or electron guns in this scenario fire at it, compress it to the Lawson criteria, and then you get your ignition, you get your charged particles magnetically directing it for thrust. So this sort of launches. The first stage engine burns for about 2.5 years. You throw away the first stage, The second stage then ignites a much smaller engine, but this is still about 50 meters across in scale. And this has about 4,000 tons of deuterium helium-3, and this will move about 1.76 years acceleration, and then it will coast for about 46 years or so, and gets to Barnard star in this case 5.9 light years away in about 50 years. So this was designed from the 1970s, and that's a pretty cool design. There are other designs we can talk about, such as this is a model for something called a Bussard ramjet. So as you can see from the data list, it has these massive propellant tanks, 50,000 tons of deuterium helium-3 fuel. Well, wouldn't it be great if we could build a fusion engine that doesn't have to carry fusion fuel on board? And that's what the Interstellar ramjet's for. And you can see it's got this huge thing, looks a bit like an antenna at the front, but actually it's a magnetic funnel. And it's actually a world ship, so you can carry lots of people on board. And what it does is there's lots of hydrogen in the interstellar medium, and it moves through space and it mops up all of the hydrogen, which is mostly protons, and it then somehow fuses those protons, so proton-proton fusion, in a nuclear fusion reactor, and then passes it through, and in principle can travel at relativistic speeds. In other words, approach the speed of light. There's a wonderful science fiction novel called Tau Zero you might want to read, where they explore that concept. And in fact, they can't decelerate the vehicle. It keeps going and it circumnavigates the whole universe. So I'd recommend reading that. The problems with this kind of design is proton-proton fusion has a very small cross section, so it's very difficult to fuse. That's why for experimental reactors, we look at things like deuterium-tritium fusion, because that has a larger cross section, so it's easier to fuse. The other thing is those protons, because they're higher energy, you have to moderate them down before you can even pass them through the fusion reaction. And this picks up a lot of drag as it's moving through the interstellar medium. And some calculations suggest it may, in fact, not actually be able to accelerate because of that drag. So it is an interesting concept. What I would encourage you to look at is some of the more exotic systems. So you might have seen the film Passengers. And this is a model of the Avalon, which is based on the sycamore seed. So you might have seen sycamore trees that fall from the oak trees and they sort of helicopter down. And that's what the design intent was for this spacecraft. What I want you to do is perhaps go and look online up about the Avalon and see if you can figure out how it works. I think they were claiming it would move at something like 50% of the speed of light, had some kind of fusion engine in it. But if you have a look at this design and think about how it actually works, and do some propulsion calculations yourself. You know, I'm sure you're looking at things like turbojets, ramjets as part of your aerospace mechanical engineering programs. So, you know, some energy has to come in here, perhaps from the interstellar medium, and something has to come out the back. So think of it from that kind of perspective. What's the function of this? What's the function of this? Does function follow form, or form follow function in this case? Have a think about it. It's a very artistic concept. If you were really ambitious, then you might want to look at this thing, which is from a film called Event Horizon, which is it's a horror film, really, horror science fiction film, but it has this massive black hole engine at the back. Okay, and how does that work? What is that black hole engine doing? Somehow folding space. So, you know, what I like to do is I like to take science fiction books or films and actually try and reverse engineer it and do the calculations using the rocket equation and other equations to try and work out what is actually credible. Could this work? You know, could you actually produce a micro black hole in something this small, a singularity? What would the Schwarzschild radius be? You can look at, this is all general relativity to really understand this. So have a look at some of those sorts of things. And what I tend to think of is that aerospace engineering is really, I call it extreme aerospace engineering, interstellar flight, because you're looking at extremes of velocity, extremes of power, extremes of energy, extremes of heat, temperature. Everything's taken to the extreme compared to any other aerospace vehicles you're likely to look at. Even if you look at things like hypersonic aircraft that fly high through the stratosphere, you know, like the SR-71 and so forth. And those are extreme aerospace engineering from conventional perspective, but they power in comparison to the problems, engineering and physics problems associated with interstellar flight. So I'd really encourage you to look at those. The last thing I would do is I was just going to show you a couple of images, which is a bit of fun on my virtual background. So just to show you, so one of the things you need to do is to turn the actual vehicle concepts into credible sketches. For some reason, it comes out. Oh, somebody's fallen. So for some reason, it comes out upside down on this. This is something called resolution, which I've played around with designing. But this is an orthographic sketch, and I'm sure you're using software like AutoCAD, so you can play around with that. And then you can render that in 3D to produce something like this. Okay, so this is the resolution rendered as a vehicle concept sketch. And so this is when you start to develop vehicle ideas, this is what you have to kind of do. And then this is something else I've been playing around with called resolution. This is a Endeavor, sorry, this one. And you can see it's got these huge radiator fins. You just about see it behind me. You can see the payload at the front and the large propellant tanks. And this is kind of like a derivative of the Daedalus model that I was showing you. And if you look at its engines, it's actually got 4 large engines on the back. That's called parallel thrusting. Okay, so one engine will give you so much power, but actually you've got more engines, like the Saturn V, which have multiple engines. You can thrust a lot higher. Okay, so these are fun things to play around with, but the engineering challenges are vast. And I'll just show you. These are some beautiful paintings, which were made for Cosmos. Okay. Cosmos was a documentary with Carl Sagan. This is the Daedalus. You can just see it. I wish I could get out of the way so you can see the images better. Let's try here. And let's try this one. This is the Daedalus, which I was showing you the model of. And here we have Orion. This is a nuclear bomb propelled vehicle proposed in the 1950s and 60s. So it's got these huge pusher plates at the back, and you throw these bomblets out, and they explode, and they transfer momentum to the pusher plate, shock absorbers, and that pushes the whole vehicle forward. And then I will show you this one, which is the Interstellar ramjet, which is the model I was showing you just now. And you can see it's moving through the interstellar medium. Beautiful painting. And it's mopping up all of that interstellar hydrogen in space. Okay. So what you want to think about is there's 3 categories when you look at interstellar concepts. The first is physics. Does it obey the laws of physics? And there's a lot of fantastic concepts out there which don't obey the laws of physics. Some of the faster than light drive type stuff, for example. And then if all the physics works, and even with fusion, you know, we're still playing around with that in the laboratory, but the fusion credibility is getting very high. Once you've sorted out all the physics, then it's engineering, right? So can it pass all the engineering filters? Can you practically build it? You know, so I mean, for example, string theory in physics requires a particle accelerator the size of the solar system in order to test some of the ideas for the grand unified theory. Is that practical to build such a large accelerator, right? So, and then once you've done the engineering, then it's economics, right? So can we afford it? Who's going to pay for it? And then what's the ethics associated with doing that? So what I would encourage you to do, I'm sure you're moving on to other projects now, but if you're still interested in interstellar studies, is to read some of the papers. There's been a vast amount of papers published on the subject, particularly propulsion, which I'm interested in. And think about, you know, what does it actually take in terms of power and energy to send a certain mass to get to the stars? And also you can reverse that problem, because once you understand what it takes for us to get to the stars, you can ask, well, okay, so if there's lots of stars in the universe, and lots of galaxies, and there's lots of exoplanets, over 5,000 now, then what would it take for other civilizations to come here? And if they are millions of years ahead of us, what's the probability that they could be here or could come here? And you can ask those sorts of questions. And, you know, with our current technological state today, with everything we have in computing, in laser physics and so forth, we have a good handle on the problem. And it looks like interstellar travel is entirely feasible in the future. We will, as a species, go out to the planets, explore Saturn and Jupiter, and then eventually we will leave the solar system and we will explore worlds around other stars. That's pretty exciting. And so there's every reason to believe that if there are species out there that are intelligent, that have evolved independently of Earth, then they could have built similar machines. Okay. And so that's a fantastic possibility to consider. Lastly, I'll leave you with a thought. Leonardo da Vinci was a great artist from the 15th century, produced many great pieces of art, but also engineering. He designed tanks, parachutes, aircraft, helicopter type devices, really weird stuff. And I'm sure for the people of his time, he seemed very strange. But actually, a lot of these concepts that he came up with came to realization centuries later. They were built. And this is really interesting that he has such an insight into the future. And it must have been very frustrating for him at the time that he couldn't build them during his age, because he just didn't have the technology. And that's how I like to think about Starship engineering, is that we're not technologically mature yet to build all these machines, okay? But we're getting there, and we can now see the pathway. We can extrapolate into the future, and we can see where we're going to be with space commercialization, where we're going to be living on other planets, on the moon, on Mars, within decades. And, mining the asteroid belts, multiple nations going into space, whether it's America, China, Russia, Europeans, Australians, we can see where we're going to be. And so on that basis, with the development of an economic economy off-world, independent of Earth, the construction of these machines becomes much cheaper, right? So when I talk about, something like 1,000 tons, 10 to 20 joules of energy, equivalent to the global energy consumption of the Earth today, in the future, that price will come down for the same amount of energy, because we won't need to, for example, put lots of mass into space to build the spaceships, because the mass is already in space with all of the metals that we can mine from the asteroids. So it becomes cheaper. So that's how you have to think. You have to think about where we're going to be in the future. And it's not just science fiction. It's a part of our plausible future.